Hello, I'm RUOFF. I'm a scientist, specifically a physical chemist and materials scientist, and director at the Institute for Basic Sciences Center for Multidimensional Carbon Materials that's located at the UNIST campus in Ulsan in South Korea. So a little bit about my background. I got my PhD in chemical physics from the University of Illinois, Urbana. And after that, I was a postdoc both at Germany on a Fulbright fellowship and at IBM, and then went through a series of professional appointments, including at universities, that finally ended up with my coming to Korea to direct the center here. So we work on carbon materials, and that has been a common thread through my scientific career from fairly early on, although my PhD work was actually on something completely different. And so it's a pleasure to be able to talk to you about the topics today and a little bit of background on myself. I'll also give a Wikipedia site that tells more about me, but mostly I look forward to talking to you, including about our center and a little bit about UNIST, and then about these topics. Thank you. Greetings. I'm delighted to talk to young people about the topics that you see on the slide. For example, career in science, what it's like to do research and how we try to do research, and also what about writing a scientific paper and submitting it for consideration in a peer-reviewed journal. And the contents are shown here, so I can tell you that a career in science has been a wonderful thing for me. It's been very enjoyable. I'm going to provide just a few tips about doing research. I hope that they're helpful. And then also talk a little bit about writing and submitting a paper, as I had mentioned. So here you see a photo actually from a few years ago, and it shows a lot of our team members for our IBS CMCM Center, the Center for Multidimensional Carbon Materials, located at the Ulsan National Institute of Science and Technology. I was asked to provide a little bit of information about myself, and so I'd like to just point out that there's a Wikipedia that someone else generated about me that gives a fair amount of information about my background and so on. Okay, let's go forward to our topics. Well, at first I'd like to also mention we have 4 research groups in the IBS CMCM. Professors Balowski, Ding, and Lee, and myself. So we're all professors at UNIST and also directing research groups, and they do a lot of teaching about the same topics we have today as I do as well. And here's a nice picture of UNIST. We're just located a little bit south of Ulsan Center City. And this is a nice picture from above the campus showing our beautiful lake on the campus. Now, what is the IBS? The IBS is the Institute for Basic Science, and this was established about 10 years ago here in Korea. And you can let your eye scan through the different centers that are designated by their topical area. And you see here at UNIST, let me point out that we have 3 centers: Center for Genomic Integrity, and also the Center for Soft and Living Matter, as well as our center on the UNIST campus. Okay, with that as a little bit of background about the IBS and the UNIST, let's go ahead to our topics. A career in science. So I thought a way of asking the question, do I want to be a scientist, could be shown in the following way. You see we have Michelangelo, Herbie Hancock, and Sun Ye-jin. And what is a common thing that connects these 3 people? I remember reading about Michelangelo, and that when he would make a sculpture, he would work so quickly that the marble pieces were flying around him. And he was so intently focused on what he was doing in his art. And I'm sure the same can be said for the other people that are on the screen. The common thread is that they are very passionate about what they do. And the same is true for us scientists. So you can ask yourself the question, if you're considering a career in science, wow, do I really like this? Is this really my thing? Does this turn me on? Is this really exciting for me? Do I feel like I must do science as compared to other things? And that's how I think a lot of scientists end up becoming scientists, is they realize this is really for them. This is their passion. Do you like asking questions, discovering new things? Do you like to be creative? Do you want to understand nature? Do you want to understand what's happening around you in terms of science? And so these are critical aspects of what scientists do in our careers. And so if these things feel like a fit for you, then you're probably going to become a wonderful scientist. So I like to mention to young people that we build our scientific career in a kind of a simple way. We do science. And so it's very important to keep doing science, just as the pianist needs to practice playing the piano. And I want to also mention that I'm an experimentalist. Of course, there are many talented theoreticians and people who do modeling, such as computational modeling also in our center. And that's also a kind of laboratory science. But one thing that's very important to understand, particularly for young people as you focus on your classroom experiences, which are very important, is that the classroom experience typically, almost always, is very, very different than the actual doing of science. So it's good to have that perspective that in the classroom we want to get a good grade, we want to impress the teacher, impress our fellow students, and so on. But in experimental science, we learn by doing constantly. So we say it's experiential. It's based on experience. And this is something that's very important to keep in mind. There is actually no such thing as a failed experiment. So there's no such thing as an F in science. We go into the lab and we do something. We always learn from everything we do. The results might have been different than our hypothesis. What we learned might have been not exactly what we were thinking we were going to learn, but every experiment that we do, we can learn something. Another thing is, in addition to my emphasis on we learn by doing, we can think of a kind of a toolkit like the carpenter, and you're constantly adding new tools to your kit. Maybe the capability of doing experimental methods that you haven't done before, maybe methods of analysis that you haven't done before. And so there's always an opportunity to improve oneself, to learn more about how to do more. And doing leads to the capability of realizing how to more quickly do things and do things better and so on. Always be curious, asking many questions, and at the same time, I can say one of the exciting and wonderful things of being a new father, for any of the young parents out there, but some of the young people will become parents in the future, is when your little boy or girl suddenly starts to ask why. And they go through a period where they ask why about everything, but they don't provide any answers. And so it's kind of fun. But we scientists need to develop the ability to ask lots of questions, but also to move toward trying to answer our own questions. So for the young scientists, there's a balance between asking good questions, becoming more self-sufficient, more independent, but at the same time, it's very important to talk to older scientists and get feedback. So it's a balancing of both. And then as you grow, you become more and more independent, and you want to be able to do your own analysis as much as possible before bouncing ideas off another slightly more senior person and so on. I think it's very important for scientists, just as in any career, please try to lead a balanced life. So have a good exercise, go outside and enjoy and help Mother Nature. help others, your family, and others as well. Proper mind, body, soul is very, very important. So in every career, in every field, it's possible to slide into a kind of workaholism. But it's something to be careful about, and to keep focus on this balance. And enjoying your science means you're also enjoying your lives. It's important, in my opinion, to have a network of both friends and professional colleagues that you would consider perhaps a friend, but in any case that you respect them and they respect you. And so I think that there are examples of brilliant scientists who work entirely in isolation, but the more typical situation, and also helpful often to one's career, is the other people that you are connected with and how you interact with them. So I think that it's very important to not fall into the type of habit, let us say, where you go out to lunch every day with the same 3 people every day for 6 years in a row. How about mixing up a little bit and once or twice per week calling up someone else or bumping into someone else and say, I'd like to sit down and talk to you about whatever, perhaps also science together, and share with you and so on. I think this is very important to broaden our experience, but the network that you have, it doesn't have to be extraordinarily large, too large. Social media makes it possible sometimes to think we have a bigger network than we really do, but those people critical to one's career, you should respect them, they should respect you, then that can be very helpful to you. How about the actual doing of research? So you're going to see some repetition in my talk. I'm simply going to repeat some of the same points that I made before. Experimental science, we learn by doing. We keep building our capabilities. And it's very hands-on for experimental work. So don't let someone else do all the hands-on stuff and you're sitting watching them. Say, oh, I'd like to do that too. It might be an instrument that is so specialized and expensive that only the operator is allowed to use it, but please don't hand your sample off to that operator and then go somewhere else. How about, I'm so excited about what you do and how you take data with this instrument. If you don't mind, I'd like to sit next to you and just have that experience and be able to talk to you also while you're collecting the data on my sample. But many times we have the possibility of learning that instrument ourselves, or our friend might say, oh, I could do that for you. Most of the time, the best answer is, that's nice. Maybe you could sit in while I'm learning or teach me. Or if there's another operator later, I can ask you questions so I can do it myself. I think I want to make a special comment. Maybe 15 years ago, I wouldn't have specifically noted this, but computational methods are becoming so useful and so ubiquitous and so powerful that I advocate experimentalists also learning some of the computational methods, like how to do ab initio or density functional theory calculations, and actually be able to do them for molecular systems if you happen to be a chemist, and so on. So I think the modeling is going to grow and grow in importance, but the experiments become ever more valuable because the experiments are, in a sense, reality. We need to have the experimental data before we really know, a lot of times, if the computational data is meaningful. So there's a critical interplay. But now, 2021, I advocate that experimentalists should know how to use some of these theoretical methods. The packages are becoming more and more user-friendly. And I think it's very important just re-emphasizing this aspect about being connected to older scientists so that they can give you advice, but not becoming dependent on them. Having this balance between trying to do as much as you can, but then you definitely need feedback. That's very important for a young person. So this dialogue between the young and the more experienced is something that's very important in science. And when I say experiential, we don't see situations, we're not aware of them, where a 5-year-old writes an incredible novel or probably does an incredible work of art like sculpture or painting. There have been 5-year-olds who have written beautiful compositions of music and have done mathematics, so there are a few exceptions, but they also benefited enormously from gaining experience, and they simply became even better when they were older. But in our situation, we don't do great science when we're really young, like 5 to 10 years old. We do, hopefully, exciting and fun and strong contribution and maybe great science by learning a lot to build up our intuition so we can realize what's important to work on and so on. Another thing is research really should be fun. It should be maybe not a daily basis. It depends on how things are going. Sometimes things are frustrating. Sometimes the experiments, even though we mentioned there's no failure, they don't work as well as we wanted them to, etc. But by and large, it's nice to have the perspective that, hey, this is also supposed to be fun. This is a really fun thing, doing this science and learning new things and so on. So that's a nice thing to keep in mind. And we really want to a degree, enjoy doing science. A really important thing that I think young people have to experience just firsthand is that it's very important to look at your data and let your data speak to you. So it's very common for everyone. Everyone can do this, older scientists, younger scientists. Our hypothesis, what's in our mind, starts to fool us, and we start to think that's what should happen. But the data is what happens. And the data is Mother Nature speaking to us as long as we've done experiments reasonably well and the instruments are reporting things as they should be, they're not broken, and so on. Then the data is very, very powerful. So that's why we really want to follow our data. But at the same time, our data might not be valuable to us in the sense that perhaps we're not doing the experiments we need to do. Perhaps that's what the data shows us. So we might re-equilibrate and realize, oh, actually it's a different type of experiment we need to do, and that takes us in another exciting and interesting direction. So it's important to be flexible as a scientist, to be very hardworking and persistent at times, but also at certain junctures, we need to be willing to go in a different direction and try something different, depending on the project. I'd like to make a special comment for people who are at that point of their career where perhaps they've gotten their PhD, perhaps they've done a postdoctoral fellowship, and they're going to become a young professor or active in a central research and development laboratory, perhaps in industry and so on, or a national laboratory. And I think one thing that can happen to such young people is they start to think of themselves as a manager. And you're managing young people, and you're teaching them. But at the same time, it's very useful for new, young professors, national lab workers, people in industry, to make sure they are going into the lab. Go into the labs yourself for a certain amount of time daily and ensure that you're working. You're your best researcher for a certain period of time. And then eventually you segue to where you might have postdocs and so on who are extremely talented and on par with you. And so I really want to emphasize that's something that I think is very valuable for the young professionals to keep in mind. Okay, now I'd like to say a few things about writing and submitting a paper. And this is a big topic unto itself. I know some research groups have, maybe in the spring and fall, 2 or 3 day sessions for all the newcomers about how do we write a scientific paper, because it's not easy. And the first time is always challenging. I don't care who it is, you know, among my, so to speak, most talented students, or the students who were struggling a little bit but still did fine. For all of them, and for me too, the first time through writing a scientific paper is a kind of strange experience. It's not creative writing. It's not sports writing and how many exciting adjectives we can use. It's something different unto itself. So how do we try to get this done our first time through? And I mentioned there's a variety of opinions about this, so I'm giving mine. And I think the first time a person writes a scientific paper, you should concentrate on the figures and the figure captions first. And then when you think you've finished a pretty good draft of those, then stop and talk to your co-authors, the senior scientist, perhaps your advisor, and then go back and do the figures and figure captions again, and then same cycle through several times. And then the next would be to prepare the methods section. This is sometimes referred to as the experimental section. What methods did we use? What chemicals did we use? Who did we buy them from? What purity were they? There's a certain way to lay all that information out. And the goal of the methods section should be that anyone else in the world could buy the same reagents, could use the same type of equipment, could sort of read your methods section and repeat what you have done in the laboratory and generate similar results. So we'll come back to repeatability as one of the central core issues of good science. So we go through the cycle with methods also, and one can look at method sections from other papers that are published, and then you realize how detailed they are and how important it is to put everything in possible. Then finally we turn to the heart of the paper, your results and your analysis of them and your discussion for the reader to help them understand what you've done. What is the science that you've actually done? That's all in the results and discussion. And now you're ready to center that around the figures that you've made and to focus on discussing the different figures, because those are your results and tables and so on. Now what's very interesting is a lot of young people end up realizing, oh, there's some gaps. Don't feel bad. Even the most experienced senior scientists, when they write the draft of the paper, that is a way of learning. We haven't done all the science. So we're going to go back in the lab more than likely, and then we're going to end up generating some new figures and so on. So that's perfectly normal and expected, and so be ready for that. That's going to happen. Then when we finished those items at the top, believe it or not, it seems like it's somehow backwards, but then we're ready to write the introduction, the conclusion, and the abstract. It's very natural for someone the first time they're writing a paper to start with the abstract, but we can jokingly say, how can we abstract to abstract something? How can we abstract our paper when we have not written the paper yet? So the abstract is done last. The abstraction of what's in the paper, particularly the results and discussion, should be abstracted. The abstract is not an introduction. The introduction is separate. So these things come, introduction, conclusion, and abstract, and the constant referencing, insertion of references comes as we go forward with writing the paper this way. But these days, compared to looking at papers maybe from 80 or 90 years ago, we have something else that's really important. Most journals have a space limit. You only have a certain number of pages to tell your story, but it's not enough. You can put a tremendous amount of information into supplemental information document, and almost all scientific journals have this option now. And that should be treated as seriously as the central text, the manuscript itself. Manuscript, supplemental information. We've had supplemental information documents that have been 70 or 80 pages long, with an enormous number of additional figures and data and descriptions and so on. Why? Because manuscript and supplemental information, and then that supplemental information might include movies and that sort of data as well, it all contributes to repeatability. So we want other people to be able to do what we have done. That's really incredibly important, and I think it's somewhat overlooked today at times in science. You know, if I read someone's paper and I cannot understand it well enough that I could say, I could go in the lab, or talented people in my research group who have experience, etc., could go in and repeat this, then in my opinion, that's a failed paper. The authors didn't succeed in one of the central goals of science of providing a scientific paper that could then allow for the work to be repeated by others. Finally, of course, we need to be aware of the format of the journal that we're submitting the paper to. And so that will be a part of, that can come a little bit later, and then you adjust a bit in terms of formatting, etc., to meet the expectations of the journal. Otherwise, they will turn it back to you and say, please meet our format, and then resubmit your paper. I also would like to finish by strongly recommending that all of you please read these articles by Professor Emeritus Peter Thrower. Now, Peter Thrower was editor-in-chief of the journal Carbon for a very long period of time, while also a very talented physicist and who studied a lot of aspects of carbon himself. And he also edited a very large number of volumes of the Encyclopedia of Carbon, Physics, and so on. So Peter, during his role as editor of the journal Carbon, decided to write and help people understand how to write these different parts of a paper. So I also think that this will be very useful for you. So thank you very much. Good luck with your career as a scientist and in terms of doing research. And you know, if we don't write up what we do, no one ever hears about what we did. So that's a big part of what we do as scientists, is we distribute that information eventually. Thank you.